Okay, section 3.3, common factors of a polynomial. So there's a reason why we've been looking at factors and prime factors of different numbers up to now. And the reason is that we now need to start applying that to some algebra. Some of the skills you may have already, like distributive property, you should have seen already. You should have seen a little bit about algebra tiles, which we'll look at again. But here we go. So factoring and expanding are inverse operations. So if we're looking at factors using arithmetic or numbers, okay, strictly numbers, factors are the two things that when multiplied together give you a number. Okay? And when we multiply those factors together, we get that value. If we want to factor a number like we've been looking at, we take that number and we try and find two other numbers that multiply to give that. So you can see how those are inverse operations. The same works with algebra. Okay? If we're going to be expanding, so it's a different terminology now, if we're going to be expanding, we use what's called the distributive property in this case, and we multiply that into those brackets to give us this. If we're looking for factors, we're looking for something that will divide evenly into both of those terms in that polynomial, and we factor it out. And if we factor it out, we're left with something. Okay, so there's a little bit of change in terminology. As we start working through some of this, I think it'll become a little bit more clear. So let's dive into some things. Oh, it's a more quick review of algebra tiles. So you have to remember that algebra tiles, we have three different shapes of algebra tiles. We have these big squares, we have rectangles, and we have tiny squares. Okay? So the big squares represent what we call x squared. Oh, that doesn't show up very well. X squared. We have these rectangles, which represent x, and we have the small squares represent a 1. Okay, you should have had a quick look at those last year in grade 9 math. Excuse me. Different colors represent different values, so positive and or negative. So a lot of the times a textbook will say that red is negative and other colors are positive. So depending on what textbooks are used, you just need to make sure that you follow some kind of set format so that you don't get confused as to what's positive and what's negative. Okay. Now we'll look at algebra tiles and factoring this 6n plus 9. I'm going to do three different kind of ways to factor this. We'll look at algebra tiles last. What I'm going to look at first is using what we call the greatest common factor, which we've been looking at, right? So the greatest common factor is what we want to factor out of something. Most of the time that's always the case. So we look at 6n plus 9 and you try and think to yourself, well, what will I be able to divide this term 6n and this term 9, what will I divide each of those by evenly and be able to factor it out? Now a lot of these questions, a lot of these early questions, you'll see that they're fairly simple. And the idea is for you to understand or get to understand what the process is before we dive into some bigger, more complicated questions. So if we're going to look at this using greatest common factor, I think to myself, okay, so I can take 6n and I can break it down into prime factors of 2 times 3 times n. And I can take 9 and I can break that down into factors of 3 times 3. Now that we have our prime factors, just like we were looking at numbers and greatest common factors of other things the other day, I can say, well, the greatest common factor is the number that's common. Okay, if I take my prime factors, the common ones, 3 is my greatest common factor. Well, if I factor out a 3 from 2 times 3 times n, I'm left with 2n. If I factor out a 3 from 3 times 3, I'm left with 3. Now how can I write this now? I say, well, oops, I didn't need to erase that. 3 is my greatest common factor. What am I left with? I'm left with 2n plus 3. And that's factored using greatest common factors and prime factorization. Okay. I could also say, well, 6n, let me change my colors, 6n plus 9, and like I said before, you think in your head, okay, what's the biggest number that I can divide into both of those? Or if I use my factor tree, I can say, well, if I factor out a 3, I'm going to be left with 2n plus 3. There's nothing else that I can factor out of those at all, so I can't go any further. So I'm just left with 3 times 2n plus 3. Make sure that's in brackets. And of course, we don't have to write that multiplication symbol in there. 2n plus 3. And that again would be factored sort of using a factor tree. Okay. I tend to try and do most of my factoring using this method. Eventually, I think after some practice that you will also be able to, well, easily, not easily, but fairly easily look at terms in a polynomial and be able to figure out what you can factor out of those. If not, the easiest method is to use the greatest common factor method, write out your prime factorization, pull out the commonalities, write down what's left over. Okay? And with more practice, it'll be okay. Now if we look at algebra tiles, oops, algebra tiles, oh, I'm on eraser, that's why. Algebra tiles, I take my term 6n plus 9, and these are all positive, so I'd have all the same color tiles, but I would take my 6n tiles, which would be 6 rectangles, 3, 4, 5, 6 rectangles, and I would take my 9 small squares. Let me see if I can do this quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9. And assuming these are all positive, and I'm going to shade them in just for fun. So there's my tiles, and I take all these tiles, and what I want to do when I'm factoring using algebra tiles is I want to arrange these into a rectangle. Once I get a nice rectangle, I'll tell you what the next step is, but what I do is I take these tiles and I try and arrange them into a nice rectangle. So it would look something like this. Well, one possible scenario. 1, 2, and I'm using a little bit of a space between them just so that I can denote that those are my different tiles. But you could arrange these and have them touching all side by side, but it would be really hard to see the individual tiles. 1, 2, 3, 4, 5, 6, 7, not 7, 1, 2, 3, 1, 2, 3, 1, 2, 3. And in actuality, what that would look like using actual tiles would be something like this. Here's your rectangle. There's my 6 rectangles. Not very square, but there's my 9 squares. That's what it would look like. But here, I'm showing a little bit of space just so that I can see the difference between each of the tiles. So once I have my algebra tiles arranged in a rectangle, I look at the dimensions of that rectangle. I look at my length, and I look at my width. And it's those dimensions that tell me the factors of this polynomial. Here, this dimension represents x. This dimension represents x, or in this case n actually, right? I guess I should keep it consistent. In this case it's n. So if I'm looking at this dimension, it would be n. This dimension would also be n. And of course my bracket here was showing me the length. So this would be 2n. This dimension on the small square would be a 1. This would also be a 1. This would also be a 1. So this would be 3 plus 3. Over here, this is a 1. This is a 1. This is a 1. Represents 3. So my factors, 3 times 2n plus 3. Because when using algebra tiles, it's the area of this rectangle that represents the polynomial, and it's the dimensions of that same rectangle, I don't know what use red, same rectangle dimensions that tell us the factors. So 2n plus 3 times 3, or length times width, give us the total area of that rectangle, or the polynomial, 6n plus 9.